Am I audible?
Yes, sir.
Can you hear me?
Yes, sir.
Yeah, can anyone let me know if you can hear me?
Yes, sir. I can hear you.
Hmm.
We can hear you, sir.
Can you hear me?
Yes, sir.
Let me just see. Am I audible?
Yes, sir. You're audible.
I can't hear anyone. Oh, why? Let me
Someone type a message, I think.
okay, fine. Aditya has messaged that I am audible, but I can't hear anyone. So, can someone say something?
Is this audible?
Yeah, I don't know why I can't hear anyone. Uh,
Can other people hear me?
Yeah.
well, okay. Anyway, at least you can hear me. My speakers are turned up to full volume. That's not an issue. Other people are audible, but why can't I hear any of you? Hmm. Okay. So you'll have to, if you have any questions, I guess you'll have to respond by chat because I'm unable to hear you. Um, okay, so let's start. Actually, I don't know. It's a bit weird. If I'm unable to hear you, I can't proceed. So uh, let me just leave this meeting and come back to this. Okay. Yeah, can you say something right now?
Yes, sir, we can hear you.
Okay, great. So I can hear you as well now. Fine. So let's start. Wasted quite a bit of time on that. All right. Now, I wanted to start the section on flows, on the flow association, but even though it's not essential, I have to sort of take a diversion and deal with something which I was planning to do later on anyway, because so this is so the overall topic we are going to talk about is still flows, but before that, this is not really a digression because we will. It's a digression for now. So I want to talk about solutions to linear systems, which is what actually Perco starts with. Perco's first chapter is all about linear systems. And so here the setup is you have a matrix A, and I'll use this notation MNR. Set of n by n matrices with real entries, and this you can't see the screen. Let me just see whether I've shared the screen. Oh man, yeah, sorry. So I have to share the screen. Let's see. Can you see the screen now?
Yes.
Okay. So I'm going to talk about solutions to linear systems, and so I'll use this notation. MNR will denote the set of n by n matrices. Now this is a vector space itself, a vector space, and of dimension r n squared. So this can be actually identified with Rn squared. In the obvious way. So if I have a n by n matrix, I send it to, I just put all the rows side by side. And AN1, AN. So I get an n squared tuple of real numbers. I can do the same with columns. I'll get a different identification. So this map from this is from MNR to Rn squared is a linear isomorphism. So, but it's more, it's even though of course one can think of any finite dimensional vector space as a Euclidean space of some dimension, you lose some intuition when one does that. So one doesn't normally think of MNR as Rn squared. For instance, if you think of it as Rn squared, the fact that you can multiply matrices and get another matrix is not clear. that there is special multiplication operation here is not evident when you think of just Euclidean space. So a linear system is of this form. By definition, x dot equal to ax, and then x of 0 equal to y. So then we want to solve the system. Fortunately, one can do it very explicitly. And to do that, so we have to take the intuition comes from looking at n equals 1. So in this case, x dot equal to ax, where a is not a matrix, but it's a 1 by 1 matrix, let's say, just a real number, x0 equal to y. We all know what the solution is in this case. So x of t, comma y, our notation, which indicates that we are looking at the solution whose initial value is y, is a is y times e to the at. So surprisingly, the simple-minded thing example tells us what to do in this higher dimensional case. The key here is that is there an analog of e to the at in this setting? So in other words, is there something like can we talk about the exponential of a matrix? And moreover, does it have the same properties? Will it be differentiable as a function of t? And when I take derivative with respect to t, here in the one-dimensional case, the main thing is that when I differentiate e to the at, I get a e to the at. Now, suppose we are able to define this. Will it continue to be the case that after differentiating it with respect to t, will I get a e to the ta? So all that answer to all this will turn out to be yes, and that's what I'll discuss now. So exponentials of matrices. So let's take a matrix MNR. By the way, if you are able to do all this, if you are able to define e to the ta, then again one would expect the answer here to be of the form e to the ta. This is going to be a matrix now, but I want to get a column vector. So I'll multiply it with y. Just like here. So the starting point is this exponential. You might have seen this in other courses. It's a very extremely useful thing to know. And so what is, so we want to define e to the a. So what we do is, we'll try before I do that, e to the a is going to be defined by a power series of matrices. By a, well, I shouldn't say power series, but it's going to be defined by a series. And so the point, one has to make sense of convergence and so on. So for that, one needs a norm on this vector space. as I said, MNR can be identified with Rn squared. So on Rn squared, we have the usual Euclidean norm. So that makes perfect sense on MNR as well. The Euclidean norm of a matrix, which would be just square root of the sum of squares of all its entries. That gives a perfectly fine norm on MNR. But that's not the most convenient one. The nice appropriate norm here is the operator norm, which I've already mentioned briefly. Remember when we were doing that calculation about showing smooth dependence on initial data, at some point I had to use the operator norm. If you look at your notes, it's there. But here we'll need it in an essential way. So what is the operator norm of a matrix? Well, it's just norm A is so for all vectors less than or whose norm is less than or equal to 1 of AV. So you take, so V in Rn, V is a vector in Rn. And when you act A on that, of course, you'll get another vector. So here, when I say norm V or norm AV, I just mean both of these are Euclidean norms, or Pythagorean norms, Euclidean norms. But that's just a choice. If you had taken some other norm on Rn, we would get a corresponding operator norm. So the operator norm is going to depend on which norm you have on your underlying vector space. And what else? Right. So I leave it to you to check that. This is indeed a norm. So the three properties of a norm are satisfied by this. Now, for us, the two main things are, the first one, again, I had already mentioned that earlier, but let me write it again. So the first one is almost by definition. So norm of AV is going to be less than or equal to norm A, norm V for any V, for all V. And the second one, which I didn't mention because I didn't need it earlier, is that norm AB less than or equal to norm A, norm B for all AB in MNR. The second one is the reason why we, one of the reasons why we work with the operator norm. As I said, the Euclidean norm of a matrix also makes sense, but you can check that if you try the Euclidean norm, this inequality is not literally true like this. You'll get a constant somewhere here. But with the operator norm, you don't get any constant. So it has this nice form. And that makes it easier to work with. So the proof is One is almost by definition follows from the definition of norm A. The thing is that so we from the definition, if I know that if I act A on a unit vector, let's say V divided by norm V, this will be less than or equal to norm A. Because norm A is the sup over all vectors whose length is less than or equal to 1. And here I'm acting A on a specific vector of length equal to 1. And this is for all V not equal to 0. So this immediately implies that this less than or equal to, so the 1 over norm V comes out, and then I'll put it on the right side. Second one, the property also is more or less from the definition. After all, so I want to so let's calculate the length of this. AB acting on V, where norm V is less than. So I'm just going by definition here. So start with any V with norm V less than or equal to 1 and consider ABV. So I just want to show that the sup over all V is less than or equal to something. Then I'd be done. Well, this is, I think of it as A BV over this. And from the previous one, I have less than or equal to norm A times norm BV. Again, the first step, the first property will tell you that this is less than or equal to norm B, norm B, which is, since I took norm V less than or equal to 1, is less than or equal to norm A times norm B. So for all V with norm less than or equal to 1, I have ABV less than or equal to this quantity. Therefore, the sup, taking sup O on the left side, I get norm AB will be less than or equal to this. So that completes the proof. Right. So this is enough. Actually, this is all. Right. I need a corollary of this, of the second one. Norm of, if I take a power of a matrix, I'll get norm A raised to K. So take B equals A and then inductively go on increasing the power. So this is all that I need actually. So in order to talk about exponentials of matrices. So the definition, e to the A is, now I can talk about limits, limit k going to infinity, j equal to 0 to k, e to the j by j factorial. So the claim is that this limit always exists, and well, actually it's much more than that, but to begin with, this for any a, this limit always exists. That would be the first claim. So, but we have much more than that. So, but let me write that for any a, the limit exists to the function from R to MNR is given by t going to e to the ta is infinitely differentiable as a function of t if in fact if f of t is e to the ta, then f prime t is a e to the ta, f double prime t is a squared e to the ta, etc. So let me prove the first. Actually, the proof of the second one anyway incorporates the proof of the first one. But let me just do the first one for clarity, in case you haven't seen this before. So let us look at let the partial sums. Let sk equal to aj by j factorial, j equal to 0 to k. Each of these are just n by n matrices again. They're just finite sums at this stage. They're partial sums. So I want to show that they converge. So for convergence, you might have seen the fact that when you are on a Euclidean finite dimensional vector space, any two norms are comparable in a specific sense. So in particular, if convergence with respect to one norm will be equal, happen if and only if it happens with respect to another norm. So in that sense, if I want to show that these converge, I might have very well dealt with the Euclidean norm on MNR. But it's easier to see this convergence in the operator norm. That was the whole point of introducing the operator norm. So let's do that. Now the catch is, as usual, we can't quite prove convergence directly since we don't know what it's converging to. In fact, the limit is what we are calling e to the a, but a priori e to the a doesn't make sense. We want to show that there is something called e to the a. In all such cases, when we don't know what the limit is, we have the basic idea that you just have to prove that the sequence is Cauchy, and then you would be done. So note that for that, note that MNR with the operator norm is a complete metric space. Because, as I said, the operator norm is comparable to the Euclidean norm on Rn square. And we know that this second one, Euclidean norm on any Rn is complete, of course. We know that. We know that Euclidean spaces are complete. Therefore, so is. But here I'm not going to elaborate on this part, the comparable thing. In case you haven't seen it, this is there in actually this is there in Apostle or any standard text. In fact, you just or even in, for that matter, even in Perco, I think. Let me see. Perco maybe not, but I can put up a small note explaining this point. But right now, let's assume this. All we need to know is that MNR with the operator norm is a complete metric space. So if I have a Cauchy sequence, I know that it will converge. Therefore, enough to prove that Sk is a Cauchy sequence. So let us take, so we want to show that given epsilon, we can choose a capital N so that when we are past capital N in the index, the terms of the sequence are epsilon close. So given epsilon, so let us choose, capital N, so that if I have two indices, M k bigger than N bigger than or equal to capital N, then Sk minus Sm is less than epsilon. So beyond a certain point in the sequence, all the terms get very close. So let's estimate this. Sk minus Sm, this is norm of summation Aj over j factorial. J will now start from m plus 1 and go up to k. And this is going to be less than or equal to summation j equal to m plus 1 to k. Use the triangle inequality. A to the j by j factorial.
Excuse me, sir. I can, there are only multiplicative propositions. We haven't proved the triangle inequality. Does it hold for the operator norm?
Well, the fact that the operator norm is a norm automatically implies that the triangle inequality holds, right?
Oh yeah, so we need to
Right.
check
So
that.
that's one of the properties of a norm.
Okay, sir, got it.
So now that, but here's the main point, more than the triangle inequality, the fact that no, here I'm left with norm of a raised to j. This is where the use of operator norm comes in very handy. I can replace that with norm of a, and then the power comes outside j because of the multiplicative property. So now we are done because we know that if you look at this usual exponential function, exponential of norm a is some real number. So if you look at exponential of norm a, we know that this converges. Therefore, we know that the Cauchy property holds for the sequence of real numbers now here. Therefore, this sum, there exists n such that, oops,
Sir,
yeah,
sir, you mean the power series in norm A, right? Power series in norm A converges to e to the norm A.
yes. Yeah, I mean, this, of course, this is a shorthand notation for saying that, I mean, the series were defined by partial sums. Basically, this norm A, this thing converges. See, when we say power series converges, it's a sort of a loose language. It just means that you have a bunch of partial sums that converges to something which we call the whatever it is. So that is understood. So we know, when I say that we know that this converges, I mean that the partial sums defined in the obvious way converges. So what is the practical implication? There exists n such that if k greater than or equal to greater than m greater than or equal to n, then precisely this, what I have above, this thing is less than epsilon. So the real number exponential function gives us this capital N that we were looking for. That's the moral of the story. So it's basically the Weierstrass M test. You don't know, but applied to Cauchy, the only main point to realize here in this proof is, a priori, you don't know what is exponential of A. You're trying to define it. So you just work with the Cauchy criterion, then use the Weierstrass M test for the Cauchy criterion, and you're done. So this, the original sequence is Cauchy. original sequence of matrices is Cauchy. Therefore, we have a limit that we call exponential of A. Well, that still is not good enough. I mean, we have, but what, as I said, the part 2 is the main thing, that we need to know that something stronger, that when I put in a T, differentiability of f of t equals e to the ta. I want to know that this, as a function of t, this becomes differentiable. Well, at least we now know that the right hand side is defined for every t. So now we fix a. A is fixed, but t is varying. So I get a f as a function from r to mnr. If you are confused about how we can talk about differentiability of f, remember that this is just Rn squared. We know how to differentiate functions between two Euclidean spaces. So it is the same old thing. But earlier on in the course, I told you that when the domain is R, so it's a function of one real variable, differentiability can be, the abstract definition of differentiability as a linear transformation, etc., turns out to be just equivalent to differentiability of all the component functions. So here you'll actually get n squared component functions. Each one is a function of t. But each one is just a real valued function of a real variable. And overall differentiability of f turns out to be equivalent to differentiability of all those components in the usual simple-minded one variable calculus sense. But what I didn't mention earlier is that, I mean, so I leave it as an exercise. If you have a function from R to Rn, let me use some other capital N. The derivative of f which is defined as, which can be, I mean, it's not defined, it is, turns out to be the same thing as this, which was what I was talking about. You just differentiate each component. You can actually, instead of worrying about components, if f is differentiable, you can directly apply the quotient, familiar difference quotient, and take a limit. So the nice thing here is I don't have to worry about components. But if you do this process, all this assuming f is differentiable, if f is differentiable, either component wise, then this can be just recovered directly like this. You do this difference quotient and then you take this, that's all.
Sir, is this true for functions of multiple variables also?
Multiple variables, this doesn't even make sense, right? I mean, the whole point is this h in the denominator. That's why we had to go through all that linear transformation business, right? So the point is that when you have a function of one variable, no matter what the target is, it's easy to define the derivative, either as component wise derivatives or as a difference quotient, limit of a difference quotient. Simply because the difference quotient makes sense in the first place. I can divide by h. If you have multiple variables, then you can't, and then you have to do that linear transformation definition.
Okay, sir, got it. Thank you.
Yeah, so this is so you can recover it like this. Yes, all right. But there are too many small details which I can't keep on mentioning because I'll get sidetracked. For instance, you have to figure out all these things. They're not very important, but they are mathematically they're important, but it should be obvious at some stage. For instance, here, when I say that this limit equal to this limit here equal to this here, the question is in whenever we are taking limits, we are using norms, right? So or distance functions, whatever. Here we are using norms. So when I say this limit equal to this, for what norm? All along we had sort of using Euclidean norms. So that this question, there was no issue at all. But notice that here for us, the target is MNR, where we are using operator norm. But again, that basic principle that it doesn't matter which norm you use, as long as yeah, it doesn't matter which norm you use as far as limits are concerned. So in other words, if limit of a certain function equal to something in a certain norm, the same thing will be the case for any other norm on the same Euclidean space. So you don't have to worry about that. But that is a point which has to be mentioned, I guess. But so the upshot is that why I talk so much about this is when I want to say that it's differentiable, I can just work with the ordinary difference quotient. That's all. So if I want to talk about different, so let's do that here. So I want to see if the limit h going to 0 e to the t plus h a minus e to the ta by h, if this is, does this limit exist? And we can see what exactly the limit is. But to do that, I need one more fact about exponentials or matrices, which is actually more general than what we need. If AB equal to BA, if two matrices commute, then exponential of e to the A, e to the B equal to e to the B, e to the A equal to e to the A plus B. So I leave this to you as a homework. So this part you can check. Just work with partial sums and you will see why it's true. This part, well, even for real numbers, there is a similar statement. Exponential of course, the first statement is trivial. Instead of a and b, if you have some real numbers x and y, there's first equality is triviality, but the second equality still has to be proved there. E to the x plus y is e to the x times e to the y. So if you look at the proof of that, the same proof will work for matrices. But we are going to apply it in a very trivial case where A is T times A. Instead of A, you have T times A. Instead of B, you have H times A. So in other words, A and B are essentially the same matrix, except for some scalar multiples. So if we apply that, then limit H going to 0, e to the T plus H A minus e to the TA divided by H. This becomes e to the TA e to the HA minus e to the TA, and I take out e to the TA, and I'm left with e to the HA minus I, the identity matrix, divided by H. Well, so now we have two things here. The second one involves, we can regard as a function of H. The first one is doesn't depend on H. So, I mean, there are lots of things going on here. For instance, that one thing is that if trivial fact, this is just saying that matrix multiplication is continuous. So if limit, if I have two functions, A of H, B of H, so both A and B you can think of as functions from real line to MNR. Yeah, actually, let me not formulate it like this. This is way more general than what I need. I need something even more trivial. So limit H going to, so what I want to say is that this is equal to, in fact, you can call it some, let's say this is let e to the TA equal to, let's say B. T is fixed, T and A let's regard as fixed. So this is limit H going to 0, B e to the HA minus I divided by H. Now the point is that this thing here, this is again a power series, again a series. So this would be A I'm dividing by h, remember that. A plus HA squared by 2 factorial, etc., which is A times I plus HA by 2 factorial, etc. So essentially, BA I'll end up with something like this. Now, what you have to observe is that this power series as a function of h converges uniformly. So we need to know that or actually there's also BA sticking in here, that shouldn't matter, but let's you should be able to take the limit past the BA sign, BA factor, but for the moment let's keep it wherever it is. If we need to know that I plus HA by 2 factorial, etc., converges uniformly in H. If we know that, then we know that it will converge, not only converge, it will converge uniformly. And the limit will be a continuous function of h. So in that case, I can just put h equal to 0 here, because whatever I get here will be continuous in h. So the limit can be replaced by the value. If this is true, then RHS equal to just BA, because when I put h equal to 0, the only identity remains. So the key point is that something like this converges uniformly. Well, it's again the same old thing. You prove that this is uniformly Cauchy. And the way you do it is, again, repeat the calculations for the real exponential function. And you'll see that why this is uniformly Cauchy. So I'll briefly mention it next time. I won't prove it, but you can try it yourself in the meanwhile. There are too many details in this for me to do everything. But the key hint here is every step is more or less based on an analogy with the real exponential function. Okay, so let's stop here. It's already. Where was I? Okay, not this. No.